Hello everyone. Today we are going to learn fabrication of nanofibers using electrospinning. In today's lecture, we are going to learn what is nanofiber, what are the applications of nanofibers, and how to fabricate nanofibers using electrospinning. And we are also going to learn what are the various parameters involved in this electrospinning process. At the end of this lecture, by practical demonstration, we will also learn this electrospinning technique in detail. Let us see what is nanofiber. A nanofiber is a continuous fiber which has diameter in the range of nanometer. To give a broad idea about the scale difference, when we compare this human hair, which is 80,000 nanometer, we can see the nanofibers how small it is. We can also understand the scale difference by comparing the animal cell versus nanofiber. You can see here the size of the cell is in the range of 10 to 20 micrometer when compared to the nanofiber, which is 100 nanometer. So, what are the unique properties of nanofibers? Nanofibers are very small in size, which gives them unique physical and chemical properties, so that allows the nanofibers for various applications. Nanofibers also have a huge surface area compared to their volume, and these nanofibers comes under 1D material, that is one dimensional materials. It means it has 2 dimension at nanoscale and the remaining 1 dimension is larger than 100 nanometer. The nanofibers have wide application. Out of that, I will talk about some of the important application. The first application is tissue engineering. The nanofibers which mimic like your ECM, that is extracellular matrix. So, it can act as a scaffold for tissue engineering application. And we can also use these nanofibers loaded with anti-cancer drug or any therapeutic material, which will be very useful for controlled drug release. And we can also use these nanofibers for air and water filtration. We can also use it for wound dressing application. When you are using a biopolymer like silk, it can be useful for wound dressing application. It can prevent the scar formation and also it provides antibacterial shielding. Nanofibers can also be useful for sensing application. It can be useful for chemical sensor or gas sensor, and due to its higher efficiency in fluid absorption, it can be useful for hemostatic devices. And we can also use the nanofibers in food industry for making edible packaging and biodegradable packaging. We can also use it for other applications such as energy storage device or cosmetic application. We can make the face mask, or we can use it for skin healing therapy. We can use nanofiber based products. How to make these nanofibers? There are 3 methods to make the nanofibers. The first one is self assembly, the second one is phase separation, and third one is electrospinning. So, out of these 3 techniques, the electrospinning is a simple and widely accepted method for making the nanofibers. Before I talk about electrospinning, let me briefly explain about melt spinning. So, let us see how to make the nanofibers by melt spinning technique. Some of the nanofibers can be made by melting polymers and spinning them through very small holes. As the fiber spins out, it stretches smaller and smaller. So, let us see a simple example for understanding this concept. Most of you might have seen this cotton candy. The principle is similar to the cotton candy. How we make the cotton candy? The vendor add the sugar crystal here, and the sugar will melt and the polymer solution will be spun out through the tiny holes. As the fiber spins it, it is pulled thinner and thinner, and what you get is the cotton candy. The principle of melt spinning is similar to this. I hope you understood the concept of melt spinning. Let us move on to the technique, that is electrospinning. How electrospinning can be useful for making the very smaller size fibers, that is nanofibers. Electrospinning is a electrohydrodynamic technique in which a liquid droplet is electrified to create a jet, which is then stretched and elongated to form small fibers. This is a horizontal electrospinning setup where your spinneret and collector, these are kept in horizontal. Let us see the electrospinning technique in detail. Here the syringe is loaded with the polymer, and when you apply the high voltage power supply to the spinneret, what happens is an electrostatic potential is applied between the spinneret and collector, and the polymer is slowly pumped out through the spinneret, and the droplet is held by its own surface tension at the spinneret tip until it gets electrostatically charged. After threshold accumulation of the charges, the polymer fluid assumes a conical shape, and thin stream of fiber eludes from the droplet. This conical shape is called as Taylor cone. It is named after the scientist. This is a vertical electrospinning setup. You can see the collector and spinneret is kept in vertical. The electrospinning technique have more advantages when compared to the other methods. It is a simple technique and we can combine the polymers at monomer level, fibers level and scaffold level. For example, we can also make the core shell nanofibers. In the core, we can load one type of anti-cancer drug, and in the shell, we can load another type of anti-cancer drug. We can make the core shell nanofibers using the coaxial electrospinning setup. We can also use a different kind of electrospinning setup for various application. We can control the fiber diameter by simply adjusting the concentration and viscosity and other parameters. Let us see what are the various parameters involved in this electrospinning process. The parameters we can divide into three types. The first one is solution parameters. Under the solution parameters, the concentration of the solution, conductivity, viscosity, solvent volatility, surface tension and molecular weight. Under the process parameters, the distance between the tip and collector, voltage and flow rate and the collector type. The collector type, this is a stationary collector, and we can also use this kind of rotating drum collector if you want to get the aligned fibers. This I will discuss later in detail. And third parameter is the environmental conditions, where the humidity, temperature, pressure and the local atmospheric flow will play a very important role. Let us see the parameters one by one in detail. The first one is polymers. There are three types of polymers used in the electrospinning. It is classified based on the source. It can be a synthetic polymer. As the name implies, these are man-made polymers designed to meet the application requirements. Some of the examples are PCl, that is polycaprolactone, or PVA, that is polyvinyl alcohol, or PEO, that is polyethylene oxide. So these are inexpensive, so easy to fine tune these polymers for its various mechanical properties, and the degradation rates also can be modified by simply mixing with the different combination of the polymers. And next one is the natural polymers. Under the natural polymers, gelatin, collagen, so these are obtained from the natural sources. This will be very useful for the tissue engineering as well as for the various biomedical applications. And third one is the semi-synthetic polymers, where it is a combination of natural polymers, but these are chemically modified. For example, we can treat the cellulose with the acetic acid, it becomes cellulose acetate. We can use this semi-synthetic polymer for various applications. So these are some of the applications which I tabulated for our easy understanding. The natural polymers, semi-synthetic polymers and also the synthetic polymers. The applications are denoted as DD means it denotes drug delivery application, E denotes the energy, and F for filtration, and FE for food packaging, MD for medical devices, and T for tissue engineering application. So we can select the right polymer according to your final application. The next important parameter is applied voltage. The applied voltage is one of the important parameter in the fabrication of electrospun nanofibers. In the electrospinning process, a voltage is given to the needle, allowing charges to collect and overcome the surface tension of polymer. When an appropriate voltage approaches the surface energy, the droplet shape becomes deformed and forming a Taylor cone like structure. In this picture, you can understand the droplet shape is deformed and form a cone like structure. This cone like structure is called as Taylor cone, and from here you get the nanofiber, it eludes the nanofiber. The crucial value of applied voltage changes depending on the polymer solution. If you are applying the high voltage to the polymer solution, it will stretch and forms the thinner and smaller nanofibers. But if you are applying very high voltage beyond the surface energy, that leads to bead or broken fibers. You may get the bead on the fibers or you get the broken fibers when you are using high voltage. The next important parameter is viscosity and concentration. The polymer concentration is directly proportional to its viscosity. The optimum concentration for different polymers vary according to the type of polymer and the solvent used. And if you are using the polymer at low viscosity, it leads to bead production. When you are making the fibers, you get the bead formation. And when you adjust the viscosity, And if you are having the high viscous solution, you get the fibers with greater dimension. You may get thick fibers, or sometimes it may block the spinneret and you do not get any fibers. So, the spinnability of the polymer solution is determined by its concentration and viscosity. So, let us see the role of viscosity in detail with some examples. If we have very low viscosity, there will be more bead formation. You can see there are a lot of beads on the nanofibers. And when you adjust that viscosity, you can see the number of beads are gone down when compared to the previous. And when you are using the optimal viscosity, you get the proper nanofibers without any bead formation. The next important parameter is conductivity. When you are using the polymer solution with high conductivity, we will have a high charge carrying capacity and higher tensile force. When you are using the conductive polymer, you get the proper thin nanofibers, and if you are using the less conductive polymer or non-conductive polymer, you do not get proper nanofibers. The next important parameter is flow rate. A crucial flow rate allows the fabrication of consistent electrospin nanofibers without the formation of beads. Lower flow rates are preferred to provide the solution adequate time to polarize. With increased flow rates, the nanofiber would have a shorter drying period, resulting in an accumulation of fibers with beads, and sometimes increase in flow rate with a decrease in voltage or decrease in rotational speed for drum collector will increase the diameter of the fibers, and this Taylor cone shape may get smaller when the flow rate decreases. When you are using the optimal flow rate, you get this kind of proper Taylor cone. With respect to the increase in the flow rate, what happens is you get this receded jet, or you can get this semi spherical droplet, or you get the aggregated fluid, and if the flow rate is very high, along with the cone jet you may get the unspun droplets which will fall on your fibers and it will create the beads on the nanofibers. Let us understand the role of flow rate with some examples. When you are using the high flow rate, you can see that more bead formation, and when you adjust the flow rate, you get less bead, and at the optimum flow rate there is no bead formation. What you get is very good nanofibers. And when you reduce the flow rate further, what happen is you will get the splash in fibers. It may look like a normal nanofibers, but there will be a splash in the nanofibers. The next important parameter is environmental conditions. The environmental conditions also play an important role. For example, temperature, relative humidity, these also play a very important role in the final product, that is the nanofibers. For example, when you are using the low humidity, which causes the solvent to dry and increase the pace of evaporation, and at high humidity you get thicker fiber diameter. You can see here at high temperature the polymer get degraded, and when you are using this optimum environmental condition, you get the proper nanofibers. In case of moisture, the fiber structure get deformed. The next important parameter is working distance. What is working distance? The distance between the tip and the collector is called as working distance. In the electrospinning process, a minimum distance is required to allow for solvent evaporation before the fiber reaches the collector. If you are keeping the optimum distance between the spinneret and collector, you get the nanofiber. If you are keeping the collector close to the spinneret, you get the thick fiber, or you can get the bead formation, and if you are keeping the collector further down, you get the broken fibers. Let us understand the working distance with some examples. If you are using the minimum distance, you get heterogeneous fiber. If you are using the optimum distance, you get homogeneous fiber. If the distance increased, field strength starts to lose, and if the distance is more, it leads to broken fibers. As I told you earlier, we get broken fibers if the distance is more. The next important parameter is collector type. So, depends on the collector, the final product will also vary. For example, if you are using the stationary collector, you get the random fibers, random or misaligned fibers, and if you are using the rotating drum collector, you get the aligned nanofibers. You have to select the right collector, depends on your final application. So, let us see the summary of various parameters. The first one is molecular weight. If you are using the high molecular weight, it will reduce the number of beads, and if the solution concentration is very high, it will increase the fiber diameter, and if the surface tension is higher, it leads to instability of jets, and if you are using the increase in conductivity, that leads to the decline in fiber diameter. If you are using the low viscous polymer, you get the bead formation, and if you are using the high viscous, it will increase the fiber diameter. Let us see the summary of process parameters and applied parameters. In the process parameter, the first one is tip to collector distance. There will be a formation of beads when you are keeping the distance very small or very large. We have to use the optimum distance to make the uniform size nanofibers. And if you are keeping the flow rate low, you get the smaller fibers, and if you are keeping the flow rate high, there will be a bead formation. And based on the voltage, if you are using the optimum voltage, you get the proper nanofibers. The fiber diameter will decrease with respect to increasing the voltage. Under the applied parameters, the first one is humidity. If the humidity is high, there will be a formation of circular pores in the nanofibers. And if the temperature is higher, which leads to degradation or rupture of fibers. So, let us see some of the common issues in the electrospinning process and how to overcome those challenges to get the proper nanofibers. The first one is jet formation problem. If there is no jet formation, it may be due to low voltage. Increase the voltage to overcome surface tension, and it may be due to high viscosity. Reduce the viscosity for better flow. It may be due to tip buildup. Clear the blockage at the needle tip, or it may be due to the volatile solvent. You can use a less volatile solvent, or it may be due to the high flow rate. You have to adjust the flow rate to avoid the bottleneck, and we also have to adjust the humidity levels. The next one is, if you are getting droplet formation, it may be due to the high flow rate. The increased flow rates result in the accumulation of fibers with beads, so we have to adjust the flow rate. The droplet formation may be due to low viscosity. Increase the viscosity for better fiber formation, and it may be also due to high voltage, so we have to adjust the voltage to prevent overstretching, or it may be due to the tip buildup. Clear the minor blockages and adjust the humidity. Some of the other issues related to the electrospinning process is beading of fibers or uneven diameters. So, how to overcome this beading of fibers? If you are using a drum collector, we have to increase the speed for better alignment, and we can also check the drum stability. Make sure that you are using the stable drum setup, and also make sure that there is no airflow disturbance, and maintain a consistent temperature so that you can avoid the bead formation and you can get the proper fibers. If you are getting uneven diameters, you can adjust the needle position and the distance between the collector and the spinneret. We can also adjust the voltage for optimal stretching, and we have to adjust the flow rate for consistent fiber formation. We also have to check the temperature for ideal viscosity as well as the evaporation rate. By doing this, we can get the fibers of uniform size, and we can avoid the fibers of different diameters. Let us see what is contact angle and how to measure the contact angle. When we rest a small droplet of water on the solid surface, the tangential outline of the droplet on the solid forms the contact angle. If your contact angle is less than 90 degree, that means your material is hydrophilic in nature. If it is between 90 to 120, that means your material is hydrophobic in nature. If it is more than 150, your material is super hydrophobic in nature. By this simple contact angle measurement, we can understand our material is hydrophilic in nature or hydrophobic in nature. I hope you understood the theory as well as the basics principle of the electrospinning technique. Let us go to the lab and learn this electrospinning technique more in detail. In this experiment, we will learn how to fabricate nanofibers using an electrospinning instrument. For proceeding with the experiment, the materials required are polyvinyl alcohol as the polymer, ultra pure water, beaker with magnetic bead, glutaraldehyde as a cross-linking solution, a syringe, and a desiccator. We need to prepare a 10% polymer solution. So, we begin by weighing 5 gram of PVA. Next, measure 50 ml of ultra pure water. place the beaker with the magnetic stir bar on the stirrer. Add some ultra pure water to the beaker and turn on the stirrer, setting it to 37 degrees Celsius and 400 RPM. Gradually add the PVA powder into the beaker. Cover it with aluminum foil and continue stirring. After a while, add the remaining water. Let the solution stir until the polymer is completely dissolved. Once the polymer is dissolved, carefully pour the solution into the syringe. Make sure there is no air gap in the syringe. This is the electrospinning machine where we will fabricate the nanofibers. Make sure that you are standing on this thick rubber mat when operating the instrument. Start by turning on the machine. Here is the temperature controller, which can be adjusted according to the polymer we are using. These are the different settings for the electrospinning machine. On the left side, we have pump 1. On the right side, pump 2. Next, you can see the diameter. It denotes the diameter of the backside syringe. This is the value for flow rate, where it denotes ml per minute. This is on and off settings. This is the forward or reverse settings for the syringe pump. Pressing forward rotates the syringe pump in an anti-clockwise direction. While reverse rotates it in the opposite direction. The syringe translation settings can be adjusted. We will set 60 for the forward direction and 30 for the reverse direction. First we will press home and then start, and you can see the syringe moving 60 mm forward, that is left, and 30 mm in reverse, that is right. Next, the plate translation settings. We will set 30 mm forward and 60 mm in reverse. Pressing home and start will move the plate 30 mm downward and 60 mm upward. The collector is a stationary part, but you can connect this drum to the setup to act as a rotating collector, which will rotate in one direction. We can adjust the distance between the needle and the syringe. If you press forward, it will move in the forward direction, and if you press reverse, it will move in the reverse direction. Next, in running time, we are going to set for 10 hours. Finally, we have the high voltage setup. Be cautious during this step. The red light indicates that the voltage is on. Adjust the voltage based on the polymer and the distance. Now we will begin the electrospinning process. Open the door. First, use the grounding rod to ground all components. Next, place the syringe with the spinneret in the holder. Then place the collector. Adjust the distance between the syringe and the collector. Once the distance is set, move the syringe pump forward to ensure that the polymer is coming out of the syringe. Use tissue paper to collect any excess polymer. Finally, attach the high voltage wire to the tip of the needle and connect the ground wire to the collector. Close the door. Turn on the pump and initiate the process. We can now observe the formation of the Taylor cone and the deposition of nanofibers on the collector. This is the final output of the fabricated nanofibers from the electrospinning machine. Now we will peel the nanofibers from the collector using forceps and then cut them into pieces according to our requirement. Here you can observe the side view of the nanofibers to examine their thickness. Now we will perform the cross-linking step. We will cross-link the nanofibers using a 2.5% glutaraldehyde solution. Pour the glutaraldehyde solution into a petri dish and place it at the bottom of the desiccator. Place the nanofiber mat in the desiccator . And heat it at 37 degrees Celsius for 15 minutes in a hotter oven. After that, flip the fibers. Once it is done, place the fiber in another desiccator. Leave it overnight for evaporation of glutaraldehyde. After cross-linking, store the nanofibers in a petri dish. Covering them with parafilm as they are highly sensitive. The image in this slide illustrates the surface morphology of the fabricated nanofibers. The diameter of the nanofibers is observed to be in the nanometer range with an average size of approximately 170 nanometer, and this image represents the histogram plot of the nanofibers diameter. Next, we will perform a contact angle measurement on the fabricated nanofibers. First, open the camera for imaging. Position the syringe above the designated measurement area and gradually depress it to form a single well-formed droplet. Carefully remove the droplet using the tissue paper to wipe the area clean. Place the nanofibers in the measurement area. The surface of the nanofibers should be smooth and plain. Depress the syringe so that the water droplet falls onto the nanofibers. Record a video to observe the contact angle. So in this lab session, we have learned the fabrication of nanofiber using electrospinning setup and contact angle measurement. We have previously observed the contact angle for fabricated nanofibers using the PVA polymer. In this image, we can see the contact angle of nanofibers synthesized from the hydrophobic polymer, that is PCl. Also, it is to be noted that PVA is not a stable polymer, so it can be added with some other polymer as a blend to make it stable. As a summary, in today's lecture, we learnt about the nanofibers and what are the various applications of nanofibers. We also learnt how to fabricate nanofibers using electrospinning and also the various parameters involved in the electrospinning process. By practical demonstration, we also learned how to fabricate nanofibers using electrospinning. I thank you all for your kind attention. I will see you in another interesting lecture.